Now that we can have a trick for actually solving a differential equation, let's see if we can use it. So let's suppose that we have a mug of hot water that's 90 degrees Celsius, and it's sitting on a table in a 20 degrees Celsius room. After 1 minute, the water is cooled to 87.3 degrees Celsius. How long would it take for the water to cool all the way down to 50 degrees? So one thing that you have to know about this sort of situation where you have a hot object sitting in a cool environment is that this process of cooling is described by what's called Newton's law of cooling. Newton's law of cooling that says the rate of change of the temperature is proportional to, so it's a constant, times the difference of the temperature of the object to the temperature of the environment. Okay, so of course the rate of change, so we're going to have some function here because the temperature of our mug of hot water is changing. So I guess normally we would call it capital T, but the independent variable is time, which would be little t. So then we'd have capital T of little t, which might be a little confusing. So instead of calling the function capital T, let's just call it f. So we have some function f, and the rate of change is on the left-hand side, so that's df dt, and it's some constant times the temperature, which remember is f, minus the temperature of the environment, and the temperature of the environment is 20 degrees. Okay, so we end up with this differential equation. So now that we have this differential equation, we would like to solve it, and we only have two tricks for solving this differential equation. I guess we could guess, or this equation is separable, so we could treat this like a separable equation. This equation is separable because the variable t doesn't show up at all. If you have a differential equation where the independent variable only shows up in the derivative here and nowhere else, it's always separable. So we can divide both sides by f minus 20 and multiply both sides by dt. So on the left-hand side, that gives us 1 over f minus 20 df. And on the right-hand side, we get just k times dt. Now remember, k isn't a variable. K is a constant. We don't know what constant it is. It's the constant that came up in Newton's law of cooling up here. So we'll have to find k later. But when we do our integral, remember that on the right-hand side, t is the variable, not k. So on the left-hand side, integral with respect to f, this is natural log absolute value f minus 20. On the right-hand side, we get k times t plus a constant. Don't forget your constant. Now we can finish solving for f, so exponentiate. We get absolute value f minus 20 equals e to the kt times e to the c, but let's call e to the c capital A. And a has to be positive because a is e to the c. But then we can remove the absolute value at the expense of putting a plus or minus on the right-hand side. But then we can absorb that plus or minus into a and relax this restriction that a has to be positive. So a e to the kt. And then we can add 20. Oh, sorry. Yes. And then add 20 to both sides. So f. So now we have a formula for f. F is a e to the kt plus 20. All right. Well, remember we had some more information about the function. So this differential equation, or this solution, really we got this just using Newton's law of cooling, but we have some extra information. In particular, we know how hot the water starts. So when time is 0, so at the beginning, the temperature of the water is 90 degrees. So we can plug this into our formula for F up here. We get A times E to the K times 0 plus 20. Right, so this part, E to the K times 0, that's just 1. E to the 0 is 1. So now we can solve this for, well, it looks like A is the only constant left that we don't know in this equation, so we can solve this for A. So subtract 20 from both sides, and we get A is 70. So now we know that F of t is 70 times E to the KT plus 20. All right, so that's a pretty good start. But remember, we had another data point in our cooling scenario here. After 1 minute, so I guess we haven't chosen units for t yet. Let's say t is in minutes. We knew that after 1 minute, the mug had cooled to, what was it, 87.3? Yes. After 1 minute, it had cooled to 87.3. And we can plug this t value, 1, into our formula for F. So we get 70 times E to the K times 1, so that's just K, plus 20. And now this equation, the only parameter left in this equation is K, so now we can solve this equation for K. So subtract 20 from both sides, 67.3 equals 70 E to the K, and then divide by 70, take natural log. K is natural log 67.3 over 70. And then if we want, we can dump this into a calculator. So let's see, natural log of 67.3 divided by 70. We get negative 0.0393. And change, you know, there are more decimal digits, of course. So our function is 70 e to the negative 0.0393 t plus 20. So here's the solution to the differential equation that also satisfies our initial condition. Right? When we found A up here, really we were using the initial condition to select a single solution to the differential equation from among the many solutions that we started with. Okay, so now we have a function that describes at any time the temperature of our hot water. We wanted to know when the temperature got to 50, so we can just replace the temperature here with 50 and then solve for t. Right, so this is hopefully a familiar process. Subtract 20 from both sides, divide both sides by 70. We get 3 over 7 equals e to the negative 0.0393 t. Then we can take natural logs. So natural log 3 over 7 is negative 0.0393 t. And so t is natural log 3 over 7 over negative 0.0393. And if we put that into a calculator, let's see, what do we get? So natural log 3 over 7 divided by negative 0.0393, we get about 21.56, and this is minutes. So it's going to take about 21 or 22 minutes for our hot water to cool from 90 degrees down to 50 degrees.